Hello again. On the last video, if we replace the limit x goes to c with each of these rules with the limit x goes to c minus or with c plus or even with x going to the infinities, all the above rules will still work. That is the above rules from the last video. So all these are good to go even if we replace c with a one-sided C minus or a one-sided C plus, or if we more radically replace C with positive or negative infinity. So these rules are still good, but I won't go through the trouble to list them. You would go down in these limits to these little subscripts and you would erase the C and you'd put the other guy that you want to have, whoever that would be, or the other symbol you'd want to have. Okay, just letting you know that, just for the sake of completion. And again, for my sanity, I will not list those. That would take up a lot of time and to be almost silly. But anyway, we define next, moving on, change of the guard. This is going to go back sort of to a horizontal asymptote concept. We define the number e to equal the limit as x goes to, just pick either infinity, 1 plus 1 over x to the x, and we take its existence for granted. I'm not going to prove that it exists, but it does. It's a unique limit. This limit exists, it's finite. It equals a number called e. E is roughly, it's irrational, and it's roughly equal to 2.71828, but that's not precise, okay? It actually goes on forever. This is just a mere approximation, okay? Don't use this approximation often, though. Type e in your calculator in order to avoid grief. We assume without proof that the limit x goes to 0 of sine x over x equals 1, and we assume without proof that the limit x goes to 0 of 1 minus cosine x over x equals 0. Guys, I did this in a previous example, and what I'd like you to do in that previous example, go ahead and we take this for granted already. I really should have put this above that. When I did that composition example of composite functions or substitution, it was one of the two. I used this. I should have told you, but I took this for granted. That this limit equaled 1, and I went ahead and I remember I defined a function that equaled sine x over x for non-zero x, and that it equaled 1 on the other hand when x was 0. I did that to ensure continuity. I was taking this for granted in the woodwork, okay? That shouldn't cause you trouble, but just I was assuming continuity from the go, okay? So now, as such, the function f from r to r such that f of x equals sine x for non-zero x, here it is, and f of 0 equals 1, it's continuous to any real number, including 0, because at 0 we break away from this and we define it to be 1. As it turns out, if you plot this on a graph, you can graphically show that this is true, that if you define f of 0 to equal 1, you will have continuity even at 0 itself. Okay. Now, the quotient and product of continuous functions is continuous, so, we're continuous at any non-zero point on account of the quotient of continuous functions. We're assuming that rationals and that polynomials and trig functions are continuous and all that, as long as the domain is appropriate. But anyway, there's that. So that's, for non-zero numbers, that's why this is continuous here, okay? And and graphically, you'll have to draw the graph, but you'll see that you'll get a pothole unless you define f of 0 to equal 1. You'll get a removable discontinuity. But if you define f of 0 to equal 1, you will be continuous, and you'll be fine. You'll be continuous altogether. And actually, this is continuous at all real numbers. In fact, this is going to be a thing called the sinc function, SINC of x. It equals sine x over x at non-zero x, and it equals 1 at x equals 0 itself. And sinc is continuous everywhere in its domain, so which is all real numbers, by the way. So good to go. Okay. Now, let's see. Consider the limit w goes to infinity of 1 plus 1 over w to the 2w power. Let f of x equal x squared, and let the limit y goes to infinity of this guy right here equal g of y, where f and g are defined for any non-zero real number. So they're defined, f and g are defined, well, f is defined everywhere, even at 0, but let's just leave 0 out of this because g of 0 is trouble. We claim that, okay, so that's g of y, and where f and g are defined. Okay, then f composed, you know what, g, I don't need that limit here yet, because if I went and take this limit, g of y would just equal a constant. It would equal e for everybody. Sorry about that, guys. Let me get rid of that limit. And I just want this. So ignore this empty box that shouldn't be there. I would have to go through some trouble to get rid of it. So g of y is just 1 plus 1 over y to the y, okay? Where f and g are defined, we're going to define f and g on the non-zeros, the non-zero real numbers. Then f composed g is a function from the non-zero reals to the reals. We're doing f composed g this time, such that f of g is f of this guy right here, which is, we're just going to square this guy right here. But remember, by the laws of exponents, you just stick the 2 up there with the y, and you get 1 plus 1 over y to the 2y. And we hence have, using our rules, the limit y goes to positive infinity right here of this guy. That's our composition function, as we've already found out. It's this limit right here. You can take the 2 out. But remember, the limit of the square is the square of the limit. So that's just e squared. And that's sort of the way it feels like it ought to be. And it is. Okay. Another example, the limit x goes to 0 of the sine of 2x over 3x. That's going to be 2/3 times the sine of 2x over 2x. I moved that 3 out to the side and stuck a 2 down here, but to balance this 2 down here, I have to have this 2 up here. I won't sine 2x over 2x, that way I can use my rules. I yanked the 2/3 out by the limit rules, and now I just have the limit x goes to 0 sine 2x over 2x. But now remember, you can do y substitution, let y equal 2x, and I need to put that there. So that's just letting y equal 2x. X is going to 0, y is also going to 0, so that y equals 2x. So that's limit y goes to 0, sine y over y. That's just 2/3 times, remember, that's 1. We're assuming without proof that that's 1. And 2/3 times 1 is 2/3. Okay, using variable substitution, y equals 2x, okay? And then, now here, this next guy is a change of the guard, and let me save that for the next video. Thank you. Let's close this video off.